Welcome back everyone to another interesting project video. So from the title you might be a bit confused what I'm planning to do. But yeah, I'm going to explain everything and show you what I'm up to this time. So for the longest time I wanted to actually build a neon lamp clock, a neon lamp digital clock. It's actually it's one of the oldest projects I ever started. It's what actually got me somewhat about thinking about microcontrollers and all of that. So it was kind of a bridge between, super classic analog electronics and using microcontrollers and stuff. And yeah, here was my first iteration of the display. This is pretty old. This is like 5 years old or so, pretty old. I've actually finished this display. It's ready to be used with something, but yeah, it's not really very practical in the state it is, and it's also not super beautiful, so it's basically just a test piece. And as you can see, now the wording of neon lamp clock is really understandable. It's just a 7-segment display which is made out of neon lamps. This basically just emulates Nixie tubes. It's the pretty much poor man's version of building a Nixie clock. Yeah, there's only one other person that has done this before, or almost, I think. But yeah, I'm gonna link some of the resources I find in the description. So a lot of time has passed till then, and I really wanna finally have a working clock. And this time I'm going to make the display a bit bigger. You can see here. Now I'm planning on actually making it with hours, minutes and seconds. As you can see also, this display doesn't have the same neon lamps for the hours and minutes, which is kind of cool. These are bigger, these are smaller, but yeah, for the new version I'm gonna use these same neon lamps for all the display segments, so I also don't have to choose any different resistors for the current limit of the neon lamps and all of that stuff. Alright, here's the brain of the clock. Let's see if this can focus maybe. You can see it somewhat. There you go. It's a pretty old microcontroller. It's an 8089S52. This is pretty much just because I need a lot of I/O for all the outputs for the neon lamps. I also need a BCD to 7-segment decoder, which is gonna be a 7447, I think. Yeah, it's gonna be that IC, which is gonna drive all of that. And yeah, I'm gonna explain the circuit and all of that a bit later, but we are in the inception phase right now of this project. And as you can see, I already got ahead of myself a bit and made some of the design things without filming, and now this time I caught myself before I went any further with this project. So yeah, this is gonna be the display. You can see it's gonna be about this big. It's gonna be a kind of flat clock, which is good to put somewhere on a desk or somewhere. And yeah, I think it's gonna look really well, especially because I'm gonna use my standard wood, which I always work with, which is gonna be this piece of olive wood. And it's gonna be the front panel, and I'm actually gonna carve these rectangles into the wood. So I'm gonna recess the display and the neon lamps into the wood, which is gonna look really well and work really nicely. Also, the orange glow is gonna really pop on the wood, and yeah, just wait for it. It's gonna look pretty awesome. For the back, I think I'm gonna use olive wood as well, but for the sides I won't, and for the top and bottom also not. I'm gonna use probably the same plywood I used for my keyboard. So yeah, there's that. And yeah, with this inception phase out of the way, it's time to work on the display, because that's the most important thing, and that's the first step. So you're gonna see that next. Alright, so I have now moved the workbench, so I have a better spot to throw all the dust out from the sanding. I usually sand inside the veranda, but then everything gets really dusty and it's kind of a mess to clean up. So this is my new strategy. Just choose a spot in the shade behind a tree or something, and yeah, this is my setup now. So let's roll the time lapse. And here it is. Here's the piece of wood for the display. All sanded and all almost ready for, the stencil, which is right here. It's a tiny bit bigger than the size of this paper, but that's alright. That's even better. So yeah, I have to mark this on here now and start carving the segments into this, so they have the recess like I told you about. Yeah, I'm gonna get to that. Okay, last thing you saw me do on this was drill all the holes to mount the segments in this, which the segments obviously are these neon lamps. But yeah, as you can see, this has changed a bit now. I rounded the edges, did a lot of hand sanding, and yeah, I did not record that because I think it's pretty much unnecessary. Next step is taking actually, before I glue all of these neon lamps in, I actually have to finish this, so probably next step is to either varnish this or wax it. I'm probably going to wax it. I'm maybe gonna still finish this a bit more, and then I'm gonna have to individually put these in and put a drop of glue on this side to hold them in. And yeah, I'm gonna assemble the whole display. Alright, there we are. This is the display piece after I waxed it. See that in the time lapse. Yeah, now I have to mount every single one of the segments for the individual display numbers, which you saw me drill, and yeah, this is gonna take a while, so you are gonna probably see it finished because time-lapsing this is not very interesting. It's just mount neon lamp, put it through, glue it on, wait, rinse and repeat till everything is in there. So hold please. There it is. All the segments have been completed. Nicely built into this. These are fixated now. Made a tiny bevel, or well, I just drilled with a larger drill a bit in all of these holes on the other side. Put a bit of glue in there so it holds the pins down, as you can see. Works really nicely. And now most of the mechanical construction of this display is complete. Well, actually, yeah, most, because we still have to wire it. Okay, here it is, all finished. This is now in a working state. This took forever to get right. Well, not really, it was like 2 days of constant work. Yeah, getting this neon display to work was more difficult than I thought. In the process of experimenting, I even burned the previous microcontroller out. This is a new one I have here, which is a bit different, but yeah, it still works fine. Actually, it works perfectly because the circuit was designed for this. Yeah, the previous one was the 89 S52, and this is the S51, which has a little bit less of storage, but that doesn't matter. The code is pretty simple of the clock, so it still works. Okay, so let me explain a bit why this was so complicated to get working. Well, it was mostly the high side drive of the neon lamps, which was, yeah, quite a pain to get working. It's this whole daughter board here. You can see 6 optocouplers here, which is one for each high side of the segment. And yeah, this is some complicated circuit I designed there, which I had to do from scrap and do a lot of experimentation. I worked a whole day without eating on this, doing stuff, experimenting stuff, and yeah, it's still not quite done. I still have to wire the dots here. The dot points are in the air here, not connected to anything. You can see them here. You can see all the mess behind here. There's like a bazillion resistors there, and I will explain why they are there in a minute. And yeah, besides the circuit board here has also some pretty crazy things. We have the low side drivers, we have the pre-drivers and the actual high voltage drivers. We have the BCD converter, which has some bodged resistors down here because it needed some pull-up resistors because it's not newer logic chips which need pull-up resistors which weren't in the schematic. That was another thing I had to chase. Yeah, lots of problems I had to chase down and eliminate before I got this working. And yeah, it's still kind of complicated to run. It needs 3 voltage sources to work. 1 for the logic board, 1 for the data board, and 1 high voltage source for the display. It's quite crazy, but yeah, it was necessary. Driving this is that complicated. But yeah, that's besides the point. I will explain that in the circuit and so on. I'll get to that. And yeah, I'm crazy happy this works now, and I will show it off later in the video. But first, I'm gonna explain some 7-segment stuff and some schematics theory. Let's go. Boom! Crazy theory drawing and stuff. I'm gonna proceed to talk 30 minutes over this paper now. Well, no, I'm joking, of course. Well, but anyways, where should I start? Well, let's start on the basics. We have here a 7-segment display. You can see this is numbered. Each segment has a codification with a letter, which goes A, B, C, D, E, F, G. And it's always like this. This is pretty much to know where everything is. Yeah, you can see here 1 segment of my display. This would equal to this. You can see A, B, C, D, E, F, G. 7 neon lamps, 7 resistors in parallel. These resistors are to shunt transient voltages because the wires induce voltages and this display started to flicker and stuff. I'll get to that later. But yeah, these resistors are necessary because these neon lamps have obviously infinite resistance when there are open circuits. So these resistors are here to help keep some potential over these neon lamps. Okay, you can see A, B, C, D, E, F, G. This would be the same here, obviously. 7-segment display, 7-segment display. It says it here, display segment. This is this. And now comes the interesting part. My circuit uses a BCD output on the microcontroller. So it controls this IC, which is this one here, with 4 inputs, just like you see here. And this is a BCD to 7-segment decoder. So you put in this and this comes out, and I will explain this later. So yeah, BCD to 7-segment decoder. This IC, you put this in, this comes out, and this is what the display is gonna display, which I put here, which is the decimal, 0 to 9. Okay, let's continue. So this BCD code is like you can see here. It's classical digital stuff. Everything is in 1s and 0s. You can see the 7-segment output has the codifications here with the letters A, B, C, D, E, F, G. This corresponds to all the segments here. You can see 1 would be illuminated, 0 would be off in this case. And as you can see, we have the letter 0, we have the number 0, which in BCD would be all inputs 0. That equals 0 on the display, which in the 7-segment language would be 1, 1, 1, 1, 1, 1, 0. Or A1, B1, C1, D1, E1, F1. And you can see this related over this. That would be, I have put here this to demonstrate. A1, we illuminate this. B1, we illuminate this. C1, we illuminate this. D1, we illuminate this. E1, we illuminate this. F1, we illuminate this. G is 0, stays 0. And voila, we got ourselves a 7 segment 0. And for example, if we want to do 6, we do A1, B is 0, C is 1, D is 1, E is 1. Actually, it's the rest 1. So we can do 1, 1, 1. There we go. And we got ourselves a 6. And this segment code works like this. And we have 1 0 1 1 1 1 1. But my clock actually would not illuminate this segment, which is a different way of displaying the 6. Is more like this, and the modern way is to put the extra segment on top like that. My clock doesn't do that, it just displays it like that. Also the 9. But yeah, you get the point. That's pretty much just a way to spare one segment and not have to use it. So yeah, you could modify this code to include that, which would just be A1 for a 6. This would also be 0. Can put this like this, and for the 9, in this case it would be D. That would be A, B, C, D. In this case, that would be this. You can add here a 0 in comma. Then you would be modified. That would be the modified code to do it like my actual clock does it. But yeah, this is quite interesting. You have this whole table of numbers, and this can be very useful when you program to make a 7 segment display. So you have your BCD decimal and your 7 segment code. I think this is binary BCD, if I remember correctly. But yeah, so that would explain all of this. You can watch it back if you are interested in understanding it a bit more, because I won't get into much detail, else I will end up really talking 30 minutes over this paper, which I do not want to do. So yeah, let's keep going. So how does this display control all of these pins of the neon lamps, which was the last question I wanted to answer before I got sucked into building a circuit and didn't film anything else. So yeah, we have all of these outputs, but yeah, it gets simplified to this per segment, like I told you. This is equal to this. We have our 7 neon lamps. Each pin on one side goes to 1. This would correlate to 1 in this case, because it's the first segment. This is 1, 2, 3, 4, 5, 6. So this is 1, this would be this one, and we have here our ABCD outputs, obviously. This would be the A lamp, which is this, B, which is this, here, and you get the idea. This always correlates. And yeah, this is a multiplex display. With multiplex displays are connected like this. I made this drawing here on the back so you can understand how this works. So we have again one segment, but this time I drew a second one as well. You can see again our A, B, C, D, E, F, G. This is our segment codification with the letters. But as you can see, we only gained one extra connection, which is the second high side connection of the neon lamp. Yeah, this is the high side, this is the low side. This gets pulled to ground, and this here gets pulled to plus 120-ish volts in this case. There's some resistors here, but I'll get to that. Those are the ones that limit the current. But yeah, how did we only get one extra pin if we added 7 extra neon lamps? In this case, a whole another segment. Well, as you can see, they are connected in parallel to the first one, like this. You can see, wholly connected. A with A, B with B, C, D, E, F, G. All connected in parallel to keep just 7 low side inputs. So when you connect a multiplex display, you will only get high side switches. So the more segments you add, the more high side connections you will get. In this case I have 6 high side connections, which you can also see. Like I said, there's 6 optocouplers here. 1, 2, 3, 4, 5, 6. These are the 6 isolators for the high side switching. This is all these inputs. You can see I have a ghost drawing here of the third segment that would go here, and then next. But yeah, you get it. So how does this work? Well, the multiplex is quite interesting. For example, if we want to display a 0, like in this case here, where we say 1, 1, 1, 1, 1, 1, 1, 0, it would be pretty simple. We say we pull this to 0, in this case, because it's the low side. We pull this to ground, this is plus, so the current flows through this, like this. So this would be ground, and we have plus here, for an example. So we would pull this, 0, 0, 0, 0, 0, 0, and this would stay floating, or just disconnected. In this case we say 1. This is now inverted because it's the low side. If you would switch on the high side, it would be the same as this. But in this case we are switching the low side, so it's inverted. Low side, inverted. I think you get the idea. Switches to ground, so it's 0. There's almost no potential. So yeah, we have now current is flowing through this, 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 not this one. So we have here our 0. And you would say, well, but if this is connected to plus, then these are gonna illuminate as well, right? And yes, that would be the case if we connect these to positive here. Then the current would also flow through here, 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 and here to ground. Yep. You get the idea. But yeah, that's what our high side switches are for. So these are now gonna disconnect this side. So if we want to display a 0 here, we keep this connected to plus and disconnect this one. But then you might say, how do we display 2 numbers at once? This is where the magic happens. This is where the multiplexing comes in. So we are gonna switch really fast from 1, 2, 1, 2, 1, 2. This is why the display flickers in the camera, which we are gonna see later. That's the multiplexing. This actually never connects these at once. Not even this 0 is constantly connected. It constantly does 1, 2, 3, 4, 5, 6. So it makes this. It turns this on. Then it does on, and then it turns this off. And if we say we want a 2 on this side, we would codificate this differently for the 2. Then it turns on this side to plus, zack, and then it turns on the codification for the 2, which would be a different codification. So it makes different for this side, then it switches over to this side and does the 0. 0, 2, 0, 2. That's what it does. And we have 6 display, so it does it 6 times for each one. Yeah. 1, 2, 3, 4, 5, 6. So it runs through each display, turns on each neon lamp one at a time to create the number. Then it turns off, switches to the next display, turns on each neon lamp one at a time for the next number. Then it switches to the next one, switches each neon lamp one at a time for the next number. So yeah, that's pretty crazy. But yeah, that's how it works. So we create something complicated to make something simpler, which is, yeah, That's usually how it goes with the display technology. So yeah, now you may have a basic understanding how this 7-segment display stuff works and how the multiplexing works. It's quite an interesting thing actually. Yeah, pretty clever. There's also different kinds of displays which can be even tighter than this, that utilize like for example diodes, so light emitting diodes, which you have 2 in anti-parallel on the same pin. That would be one segment. In this we can say A and B, for example, and this is the connection. Oh, sorry, I had to burp. This would be the connection. Like this, you would have next 2 segments would again be anti-parallel diodes, like this. Bim bam. We have another pin, so we have already 4 segments for only 2 pins. But for this configuration, this is called Charlie plexing. You would need to have an actual input that can supply positive negative here and then positive negative here to illuminate this and to illuminate that one, which is a bit complicated to do. You need actual a split supply if you want to make it simple, and an actual H bridge for each segment if you want to do it with a single supply, which is pretty crazy. But yeah, there's specialized ICs that can do this, and they can drive these Charlie plex displays with anti-parallel LEDs like this. And that this could actually also work with neon lamps, only you would have to connect diodes with each neon lamp, which would be even more components, which would be crazy because obviously LEDs are light emitting diodes. They already only conduct in one direction, they illuminate in one direction. They're diodes, but neon lamps aren't diodes. They can illuminate in both directions. If you connect DC, it's gonna be either one electrode or the other. That's the only thing that's gonna change. But yeah, if you want to Charlie plex a neon lamp display, you would have to connect diodes for each neon lamp, so it obviously blocks the reverse voltage for one side and blocks the positive voltage for the other side, so you can actually choose which neon lamp you illuminate. But yeah, I'm getting off topic. Charlie plexing is even more complicated to get less pins, which is kind of, I don't know, worth it for hobbyists, but yeah, it can be done if you have the specialized ICs. But yeah, there's no specialized Charlie plex ICs for neon lamp displays, because this is pretty much a novelty I came up with. Well, not really. There was one person before that came up with this and I copied it. And I'm gonna put the resources in the description, like I said. Oh boy, lots of talk. So now we are over the whole 7-segment display and how it works. So now let me explain how this freaking high side and low side driver works. This is now even more abstract for not tech or electronic versed people. So we have this crazy contraption here, which is this tiny daughter board I came up with. This is this whole mess on this schematic here, and you can see this is the low side driver. This is 1 times this and that. This is obviously 7 times on this. This times 7 is all of these transistors that are on here, which you can see there. So yeah, it is pretty simple, the low side driver. It's just complementary Darlington, because the microcontroller pulls to ground, which turns this PNP transistor on, obviously, negative PNP base to ground, equals transistor pulls to plus, turns this positive transistor on, NPN pulls neon lamp to ground. This is what would be on here. This would pull this to ground. You can see this is neon ground and logic ground. logic voltage ground. So yeah, the high voltage is referenced on the logic ground. So yeah, I could not get any circuit to work for the high side drive, which you can see here. This would be connected right here, like this, and the second one would be connected to this, like this. You can see here the small neon lamps on the drivers. This 6 times, 1, 2, 3, 4, 5, 6, like I explained. Yeah. So this high side drive was really complicated because there was some things going on with diode paths through the transistor, which were blowing up the microcontroller inputs because the potential was flying around. I couldn't get anything to really work because it was really high voltage and stuff kept breaking. So I turned back to my good old friend, the opto isolator, one of the most powerful electronic parts ever created. So opto isolator is pretty much what it is. It's a transistor with an LED in the same package. You have this phototransistor which turns on when this LED gets voltage, but nothing is connected with each other. This is an isolation. This is the component that gets used to actually regulate switching power supplies, which have to know the output voltage and compensate the whole circuitry for the primary side. And it has to be isolated because obviously you don't want to touch mains voltage on the output. So that's where the optocoupler comes in. I used 6 optocouplers here for the high side drive, which are on the daughter board like I showed you. And yeah, this gets pretty crazy because I obviously can't reference the optocoupler to the 120 volts directly, because the optocoupler only switches 40 volts because it's like a normal transistor. There are high voltage optocouplers, but I don't have no high voltage optocouplers lying around. Those are not common. These for the switching power supplies are everywhere, so I could get 6 pretty easily. But yeah, that's where the plus 5 volt for the auxiliary board comes in. So we have 5 volts for the logic board, 5 volts for the auxiliary board. This is actually not 5 volts now that I remember. This is 12 volts. I switched it higher because then these transistors switch better, which make the display run better. But yeah, it still works with 5 volt, but it's not recommended. So we have our aux voltage for these transistors, which is just an aux voltage to switch these bases on. So these optocouplers don't have to switch the high voltage. I could have implemented some Zener diode voltage drop power supply thing. Maybe I still will. Some step down converter that steps the 120 volts back down to 5 or 12 volts for the aux board, but it's not really necessary, because if I power this with a transformer, I can get like 7 billion extra transformer taps to power this, so it's irrelevant. Okay, now let me explain how this works. We have this circuitry here, which is just a high side switch basically, and we have our reference. This is ground of the auxiliary voltage. You can see it gets reference to the emitter of the transistor, and obviously this optocoupler here pulls the transistor high. This is a pull down resistor, so the transistor doesn't turn on its own, it turns it to ground. This transistor pulls to positive, which is, you can see all the collectors are connected to this 1K, which goes to the positive of the auxiliary voltage. And you might ask, why is it only one resistor? Why not one resistor per optocoupler? Well, like I told you before, the multiplexing works so every transistor only turns on once at a time, so it doesn't matter that there's only one resistor. This power source is only gonna be used once, so 1, 1, 1, 1, 1. So we don't need more resistors because we are not gonna turn these on at a time. These are never gonna be on simultaneously. It's gonna only be one optocoupler at a time. So yeah, that's why we can get away with one resistor here. And it's pretty much the same for the logic side of the microcontroller, which all of the pins of the LEDs, in this case the anode, all of the anodes are connected to plus 5 volt of the logic board over a 1K resistor, pretty standard voltage drop, well, current limit for the LEDs, and each of the cathodes is connected to one of the driving pins of the in this case, yeah, the microcontroller, which pulls these down. Actually, this is not drawn correctly. You can see here I have 1K for each optocoupler. You can see these are the 6 outputs from the microcontroller, 1K, 1K, 1K. But you could do it like this and save yourselves 5 resistors and only use 1 here, like I've drawn here. But yeah, that's besides the point. I had these 6 resistors already installed, so I made it like that. Yeah, that's how it turned out. So yeah, this is a pretty good high voltage driving circuitry if you want to switch any high voltage stuff with a microcontroller, like high voltage displays. This would be the way to go for the high side. This is pretty much the way to go for the low side. It's a bit transistor heavy and people probably would use specialized ICs, but I didn't want to build it with any because I don't want to wait on parts, nor do I want to spend the money on them. So this is what I came up with. And yeah, I tested this with 1 transistor, and I had this the negative side of the aux voltage directly referenced on this. Then I thought, wait, I can't use this because I would need 6 auxiliary voltages. But then I had the brilliant idea of just connecting it with diodes to each of the emitters of the transistors. And I do not quite understand how the diodes work, but yeah, they pretty much only reference the voltage when that particular section switches on. So it works like that, and I don't have to connect all of these together, which would completely break the circuit. But yeah, this is the circuit. It's pretty clever in my opinion, and yeah, that's what I came up with. This took me that long to get working. Actually, the circuit didn't take that long. It was mainly buttoning up all of this, building the circuit, building everything, making all this wiring like 2 times, adding all these resistors, which is what I already explained. These are the ones that kill the transient voltages because the neons have infinite resistance when they are open and not connected to anything, so they started turning on when they shouldn't, and the whole display was flickering like crazy. It still does it if I turn the voltage up too much, but yeah, it's pretty tame and good when the voltage is at the correct level, which is the only thing I need. So yeah, the parallel resistors are the transient killers. You can see here all of this, and here as well. And yeah, that's gonna conclude my explanation on this. So I'm gonna now proceed to show you how it looks. Let's go. Alright, here we go. You can see all the power supplies here. You can see the power supply for the logic board, which has the reference on the high voltage ground. The high voltage goes here, which goes to the daughter board. And this is the auxiliary voltage for the daughter board. Now we plug this wire into the power supply. Boom! There it goes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, it's 0 hours, 0 minutes, and the seconds are counting. Yeah, there it is. Clock is working. For the wiring, all the circuitry, everything. I can turn off this light. Looks even better if I put myself as shade here. As you can see the flickering. If I move the camera, it gets a bit strange. because yeah, obviously all the neon lamps are only on really one at a time. In real life, if you shake your head, you can see it as well. That's the old trick. Yeah, you can try it in real life if you have some 7-segment display near you. You can try to shake your head and you will see it strobing. So yeah, wow, 1 minute. There it is. Voltage is actually a bit too low. You can see the one neon lamp there is going out, so let me pause and put the voltage a bit higher. There it is. Now everything is completely stable. Yeah, that's about it. So I will maybe show you a bit of the design I want to do for the housing of the clock, and that's gonna be it for the video. So I will see you with the case plans. Let's go. Open the magic book. And here we are. This is somewhat of the case design I came up with. I'm gonna have the display like this, and I'm gonna have the sides swoop up like this, like wings. And some of the keen-eyed followers already recognize the theme I'm going for. This is a good implementation here. You can see this is gonna be like a shielded thing. If this comes out, you have a piece of wood underneath, and the display is gonna be recessed in here. The side pieces. This is gonna be an indentation. This is gonna be cut out. Maybe some extra neon lamps on top of here. This underneath here is gonna be a speaker, because yeah, the clock actually has an alarm feature and some other things which I didn't wire yet. There's gonna be 4 buttons to set the time, alarm and stuff. And yeah, I need to build a sound generator circuit, analog, which sounds like a nuclear alarm. And that's gonna be the alarm for the clock. And yeah, there's gonna be lots of designs. I will have to glue a lot of olive wood pieces together to make the whole case. In the beginning I said I was going to use the same plywood for my keyboard. That's now out of the question. I'm not gonna do it like that. I'm gonna glue a lot of pieces together to get the whole thing, the whole case with olive wood. So yeah, that's gonna be interesting, but all of the cosmetic things and the sound generator circuit is gonna be for part 2. So yeah, stay tuned for that. And yeah, I may still change a bit of the design, but I pretty much set this in stone. I like the idea of making the clock nuclear themed, like a nuclear timer or some nuclear display. So that's what it's gonna be. So yeah, with that, I will say goodbye, and I will see you in the next video. Later.